It's optional. Yeah. I just repeat that. Yeah. So I'm going to talk the Laplace approximation. The problem is you have a true distribution P of x, and you only know the normalized distribution f of x, and you don't know how to get the normalization constant, which means the integral is very difficult to evaluate. So this is a problem. Then we try to find a Q of x to approximate this true distribution, and we choose Gaussian distribution for the approximate. Yeah, maybe, yeah. So we use a Gaussian distribution to approximate this true distribution. So the problem is how to choose the mean and the variance so that we can best approximate this problem. So in Laplace approximation, we try to match the mode, which means the mode of the approximate distribution and the true distribution are the same. So this is object. So let's first take a look at this normalized distribution of f of x. Directly approximate this f of x is very difficult, so we choose one rhythm of fx. And we take Taylor expression of this function at point x0. And I will talk to you how to choose x0 later. So according to the Taylor expression formula, so this is fx of 0 plus the first order derivative. In this case, we suppose x is scalar, and we can extend to a vector case later. And so this is the first order derivative of x. Evaluate x equals x0 and x minus x0. So this is first order of the Taylor expression, and the second order is something like this. X and evaluate x equal to x0 and x minus x0 squared, and there is over 2 here. So this we eliminate omit the higher order, only keep the first 3 terms in Taylor expression. And now the problem is how to choose x0. We can simply choose x0 so that the first order derivative of all fx equal to 0, and by solving this equation we can find x0. So we take first order derivative of the logarithm of x and set this equation equal to 0, then we can solve this equation, get x. Right? Here x0 is the point. Make sure the first order derivative of the logarithm of x equal to 0. So this is like for example, ln x is something like this. So here is x. Here is x. Here is ln of fx. And here is x0. This x0 make sure the first derivative of ln fx equal to 0, which means find the maximum point or local maximum. The Taylor expression is okay. This is a
so we setting to 0, set this derivative to 0. We're finding the critical points.
Yeah, the local maximum.
Okay.
Then we get x0. So we can
why this is better? Choice.
Why this? Okay, I can explain you later. So now you know how to choose x0, right? So if we set x0 equal to 0, one advantage is this term has been eliminated, right? This is equal to 0. So we only have 2 terms. Okay. Another advantage is x equal to we choose x0 so that the first order derivative of ln fx equal to 0. Then we can find the second derivative of ln fx is larger than 0. Right?
Actually, I think it's more important or not this. More important is you're actually approximating around the peak. Because if your x is not close to x0, not close to then you cannot do Taylor series expansion, and you cannot approximate those higher order terms is equal to 0. You can approximate those higher order terms to be 0.
Yes.
It's really because you're thinking about x is always near the peak, right? You're basically picking x near your x0 here, and we want to pick x0 is exactly the peak because there's most likely you find, most likely it's going to happen. But this is where you have most, yeah.
So the first reason is if you choose.
If you look at the Taylor series expansion, you cannot pick x0 arbitrarily. If your x considered is far away from x0, then you cannot discard the higher order terms, right?
Oh, okay.
We can discard those just because we are considering x is close to x0. Then, yeah. Then of course we should pick x0 because we want to consider x around the peak, right? Because peak there is where you are likely to have probability around there.
But how to interpret the higher order? On the graph. So why you pick the? x0 here, you can ignore all the higher order.
You cannot even discard the higher order terms if you are far away from x0.
Yeah, but they come around x0.
Is it iterative algorithm?
No.
Or it's not iterative?
No, not right now.
You cannot write like that. Or
But
you cannot.
in theory, you can expand the.
No, you can expand, but the higher order term won't go to 0, right?
Yes.
So how can you discuss those terms? If you're really far away.
So you want to make sure that x minus x.
Yeah, that should be small, right?
Goes to 0.
Yeah, you want to make sure x minus x0 is small, right? For example, your x is far away from your x0. You can't really do Taylor series expansion for that one, right? You can't really.
Yeah, but I think this property is more important because if you don't choose this point, you will get
no, I guess
negative
no.
variance.
No, I guess.
you can expand everywhere.
Yeah.
It's not necessary to the
Yeah, but
first order
You
equation.
can around x0 actually.
No, for example, if I say I take x0 somewhere here, and I say this is x0, how can you do this very quickly?
You must
this
keep
will
the order
fail.
of
You have to keep the higher order
Yeah.
terms, right? That's what
Yeah.
I'm saying. It's more important that you can discard these higher order terms. I think this is more like a just byproduct for that, right? You cannot just
But
take
you
this
must
here.
be satisfied with this constraint. Otherwise, you
But
cannot
it's
get
just, you're
a
just lucky.
Just-
You're lucky. You cannot do Taylor series expansion. At the beginning, if you are not near your x0, it doesn't make any sense when you do Taylor series expansion of like this at here. Right? What does that mean?
So if this is the iterative algorithm, you can every time you just move a bit. So within that small range, this
No,
it's
not actually.
It's not.
It's not. It's always like setting x0 at the peak actually.
Okay.
And I think it makes sense to pick at the peak because that's where you have probability, right?
I don't quite get why long fx? Why?
Oh, it's just convenience.
Yeah, just convenience. You can get close form solution. By the end. So you will figure out that if I finish.
Okay.
And
I think it's 90. The 90 is a quadrant number.
yeah, it's negative.
So we assume there's only one peak. There's no. Peak.
No, you can have multiple peaks, but actually it's a local maximum. You can here, so you maybe have multiple x01.
Yeah, I'm not sure that would be violate your situation, violate your assumption, right?
Yeah, and in this case, we want to use
Exactly, you are looking for peaks.
yes.
Yeah.
We are looking for peaks.
Okay. So we assume it's one mode, like one.
Yeah, probably
Yeah,
one
not
mode.
possible.
Yeah, even unimode actually. Because you want to use a Gaussian to approximate a true distribution. If it's multimodal, yeah, you.
So.
Yeah, let's consider the unimodal case.
So P is known, F is unknown.
No, F is known, P is known, and you want to evaluate P of X, and but you should know the normalization constant first if you do some basic inference. The problem is Z is very difficult to evaluate, so it's very actually like given Y equal to Py, given X Py. So here is your joint distribution corresponding to the f of x here. Your joint distribution f of x. Here is the normalization constant. So you need to marginalize the joint distribution x, y, dy. So sometimes this integral is very difficult to evaluate. So this is the problem. And if we experience this rhythm of fx and set x0 so that the first order derivative equal to 0, then we can find something like this. Right. Something like this. Yeah, just eliminate the first term. And moreover, we can set it equal to minus a. This term equal to minus a. So we get minus 2a minus x. Right?
Because the x0 is peak when the first derivative is 0.
Yes.
Okay.
So if we take exponential on both sides of this equation, we get fx. So actually this is approximate to the exponential on fx0 minus 2a. Right? So what's the first term? It's fx0. And what's the second term? It's minus 2a x minus 0 here, right? So what's this? This is a normalized Gaussian, right? This is an exponential distribution. It's a normalized Gaussian.
Unnormalized Gaussian.
Yeah. And if we plug this formula into the true distribution, we get P of x equal to this over Z, right? It's an approximate.
Approximate because we remove the Taylor.
Yes.
Okay.
And since this is a normalized Gaussian, we know what's this, right?
So
This is just 1 over 2 pi times a square root. And we can write a vector case of that also. So there are two steps to use the Laplacian approximation. The first is set the first order derivative of your algorithm of x equal to 0, then you get x0. And then take second order derivative of this function and evaluate this function at x equal to 0, then you get a here. Then you get your approximate distribution with mean as x0 and the covariance matrix or precision matrix at a. So this is the whole idea.
Okay. So because this x is here, so the mean is also here.
Not mean, the mode actually, because you can only for example. This is your true distribution, P of x.
Oh yes. Okay.
And your Gaussian distribution maybe is here. Yeah, just make sure that mode. Yeah, we draw a Gaussian distribution like this. This is Gaussian, x0, and we can have a true distribution P of x like this. This is P of x. This is Q of x. Yeah. For Gaussian, the mean and the mode are the same, but for this true distribution, mean and mode are not the same. So we call this moment, match mode.
So the mode of the original distribution is mean of the Gaussian distribution.
Yeah. Yes. Yes. So this is approximation.
Okay.